here I have drawn a large cylindrical conductor and a battery. And if I connect the battery to the conductor, so if the battery has a positive and negative terminal where wires could be connected, and I connect the battery to the conductor, then I have created a closed loop where current can flow. An electric current is the movement of charges or charge through a conductor. Through a conductor. I know that charge moves through the conductor because the battery supplies what we'll refer to as an electromotive force. EMF is electromotive force abbreviated. There's something in that battery that allows the electrons that are in the conductors of this circuit to move. And if I looked at a particular point along the conductor, and by the way, the wires that are used to connect the battery to the conductor are also conductors. I've just drawn the conductor large and cylindrical like that for the purposes of the video. If I looked at one cross-sectional area, one little segment of this conductor, it would have a circular shape like this. And depending on the properties of the conductor and the properties of the battery, so things like how good of a conductor the material is and how strong of an EMF does the battery provide, there would be a certain number of electrons that would travel past this point in some amount of time, right? And so if we had a better conductor, there would be more electrons traveling past that point. If there were a battery that had a stronger EMF, or if we connected multiple batteries together, maybe there would be more electrons that pass that point per unit time. And the rate at which charge travels across that cross-sectional area, the amount of charge per unit time, is how we define the current. So current is represented with a capital letter I, and the amount of charge, delta Q, that moves past that point per unit time, delta T, is a measure of the current. That's how we define current. In summary, what I've done is I've connected a battery, a source of electromotive force, or EMF, to a conductor. And any time I form a closed loop, like in the picture that I've drawn, that closed loop is a circuit. And in a circuit where you have an EMF and conductors, an electric current can flow. And electric current is the movement of charge through a conductor, which is defined as the rate of flow of charge, or delta Q over delta T. Looking at the equation for current, the charge would be measured in coulombs, and the time measured in seconds. But instead of writing coulombs per second for the units for current, we will instead write units of amps. A capital letter A will be used to represent amps, which is the unit for current. And just for reference, a current of even 1 amps or 2 amps is actually quite significant. In most circuits, we'll be dealing with currents that are much lower and much safer, as currents of 1 amp, 2 amp are quite dangerous. We'll be working with things that are on the order of milliamps most of the time. Resistance is a measure of how hard it is to push charges through a material. So if I connect a battery to something and charge is going to move, how hard is it for that charge to move? That would be a measurement of resistance. In order to understand resistance, we need to understand resistivity. It makes sense that if I have 10 different kinds of wires made out of 10 different materials, that each of those materials would have a different resistance. if I connected each of those 10 wires to the same battery, maybe the current in each of those circuits would be different. And that's because every different material has a different resistivity. And so in this chart that I have on the upper right hand corner, there's a column here that says resistivity. And for silver, copper, gold, aluminum, there are different values of resistivity that are listed there. And you can see at the top of the list there are a lot of conductors, and for all of those materials the resistivities are very similar and they're very low, right? Because they all, the first 5 or 10 materials listed there all have an exponent of times 10 to the negative 8. So materials like copper that have very low resistivities will have a very low resistance and allow for there to be a large current. So if there's more resistance, I get less current. If there's less resistance, there's more current. And so surely there must be a relationship between the resistivity and the resistance that depends upon the physical properties of the material that I'm working with. And that relationship is given by R, which stands for the resistance, is equal to the resistivity, which is given by a lowercase letter rho, Greek letter rho, times the length of the conductor divided by the area of the conductor. And I've shown those properties down below. Right, the length of the conductor is just the physical length, and the area is the cross-sectional area of the conductor. And the resistivity would be something that you would either be solving for or would be given to you in a chart like this. And also notice for the resistivities that for all of the conductors, while they have really low resistivities, things like glass and sulfur and rubber, those things have very high resistivities because they're not conductors, they're insulators, where the resistance is very high and the charge is much less likely to flow. Things like germanium and silicon are semiconductors, which could be engineered to be conductors or insulators, and are very useful for creating electronics. So far, I may have led you to believe that resistivity is a constant value because I have a picture here with lots of numbers for different materials, and you may believe that copper always has a resistivity of 1.7 times 10 to the negative 8. That's partially true. The resistivity depends on the material. So copper will always have different resistivity from silver, and it's a property that all matter has that could be used to figure out what it is, for example. But resistivity also depends on the temperature of the material. And so if I heat up this conductor or I cool down the conductor, then the rate at which charge flows changes, and so the resistivity ought to change as well. And so you can also see in this table that I've given that there's the temperature coefficient of resistivity, which must mean there's some sort of empirical formula where if you know the temperature, then you can figure out the correct resistance at that temperature. We're not so concerned with figuring out the resistivities at different temperatures, but it is important for you to know that not only is the resistivity and therefore the resistance of a given length of material determined by what it is, but the temperature also can affect what that resistivity is. There's one more R word that I want you to know, and that is resistor. A resistor is a physical thing, a circuit element that I put into my circuit in order to make the current less, in order to prevent or lessen the flow of charge. And when I'm drawing a circuit, the symbol that I'll use to represent a resistor looks like this jagged blue line that I've drawn. And I hope when you looked at the chart for resistivity, you noticed that the units of resistivity was the Greek letter omega times meters. And if you look at the equation for resistance, it's resistivity times a length divided by an area. And if the units of resistivity is omega, Greek letter omega, times meters, then that means if you look at the units for the length and the area, that the units of resistance on the left-hand side of the equation is just that Greek letter omega. That Greek letter omega happens to be the unit of resistance, which is ohms, O-H-M-S. Resistance is measured in ohms. And it's essential that resistors exist because there are a lot of instances where, say, the socket on the wall provides a voltage of about 120 volts. And if we plugged things into there without any resistance, then most of the devices that we plug into the socket would get fried. And so most circuits are designed to have resistors in them. And by having those resistors in there, the voltage and therefore the current is made to be much less. And so resistors serve to allow us to manipulate the voltage or the current and protect devices. In summary, we learned that all materials, all matter has a property called resistivity that depends on the type of material that you have and the temperature. We also learned that the resistivity, the length, and area of a material affect the resistance, and hopefully you can look at that equation and say if the area gets bigger, the resistance gets less, and come up with physical explanations as to why that might be. The same thing with the length. If the length of the material gets longer, the resistance increases. And that resistance is a measure of how hard it is to push charges through a material. Things like copper that have low resistivities are very good conductors and allow the flow of charge because they have a very low resistance. And that it's often necessary to put resistors into a circuit, things that have some sort of pushback on the charge, something that lessens the voltage or the current in a circuit in order to protect a circuit element. And now I'd like to talk about voltage. Voltage is a word that you've used before because batteries have a certain number of volts. And another word that we'll use synonymously with voltage is potential difference. Potential difference. And potential and voltage are really the words that are synonymous here. We use the word potential instead of voltage because really when I create a voltage or a difference in voltage, then I'm separating charge. And so batteries have a separation of charge, positive and negative. And that separation of charge causes or sets up, allows, an electric field to be created. And electric fields aren't a topic of AP Physics 1, but inside of that battery there's an electric field that's present, and as charges get near or are put into that electric field, they get accelerated across it. And so there's positive and negative charge that's separated. In between the positive and negative charge there's an electric field, and as a charged particle, when I get nearby that electric field, I get accelerated across that electric field. The way I'd like for you to think about that, or to conceptualize that, is to, instead of the electric field and thinking about the separation of charge, just think of a little escalator. If I was first an electron that was traveling in this circuit, let's just say I'm an electron right here. We know that in the wires that I've drawn here connecting this light bulb and this battery, it's the electrons that are moving. And so if I was that electron right there, in which direction would I like to travel? Well, I don't want to travel toward the negative terminal of the battery. I would be repelled by that negative terminal of the battery. And so I would go this way. The current is defined as going the opposite direction as the direction of the electrons. The current is defined as going the other way. And the reason for that is when the current was originally defined as pointing one way or the other, it wasn't clear as to what was moving. We didn't know as much about the electron or how conductors worked. We just knew that something was moving. And so in physics, we define current, and sometimes what we'll call the conventional current, as, by convention, moving in the direction opposite the electrons. That's extremely important because I'm going to ask you what direction the current is in a circuit oftentimes, and you need to know what that is. And because it's the direction opposite the electron movement, then you should know that the current is always going to, we'll say, come out of the positive terminal of the battery. And so current will come out of the positive terminal of the battery and go into the negative terminal of the battery. And instead of talking about electrons moving, which is really what's happening inside the circuit, we're going to talk about imaginary little positive charges that are moving in the opposite direction. Even though by convention we talk about the movement of positive charges in a circuit, the way that we'll understand circuits, it doesn't matter whether we were talking about the positive charge or the negative charge. It's just by convention the way that we do things in physics. So, if the positive charge, the little blue guy that I've drawn, comes down and goes into the negative terminal of the battery, then we're going to think of the battery for now, by analogy, as just having this little escalator, which is going to take those positive charges and raise them up. And so the positive charges get on the escalator, and they're moving up to the top. And by moving up, they gain some energy, right? We would typically think of that as some sort of increase in gravitational potential energy. Here, really what's happening is the electric potential energy of those charges is increasing. And when they get to the positive terminal, they effectively drop off that escalator. And when they drop off that escalator, that change in that potential energy allows them to move through the circuit. And so this is what the battery does. It essentially lifts up the charges, drops them off, and allows them to move through the circuit, lighting this light bulb for quite a long time, right? It continues to do this as charges move through. What's really happening is there's a difference in electric potential energy between the two terminals of the battery, and that increase or decrease in the potential energy of those charges is what allows the light bulb to stay on and the charges to keep moving through the circuit. So when I say the phrase potential difference, what I'm talking about is the difference in potential energy between the two terminals of the battery. For an ideal battery, in AP Physics 1, all batteries will be ideal. The potential difference between the two terminals of the battery is going to be the same as the electromotive force of the battery. In reality, those two quantities are not the same, and the reason why they're not the same is because most batteries have some internal resistance. The potential difference across an ideal battery is equal to the electromotive force. The way that we're going to symbolize voltage or potential difference is with the symbol delta V. So potential difference. The potential or the voltage is represented by V, and the difference is given by the delta. That potential difference across the battery is equal to epsilon, the electromotive force that is provided to the charges as they move through that battery. Most of what I've described, the conceptual nature of what's happening to all the charge, is mostly topics reserved for AP Physics 2. Here we need to know that in order to have a circuit, I need to have something that provides a voltage, and that sometimes I'll use the phrase electromotive force or potential difference to describe that voltage instead of just saying the word voltage. I don't know if this makes this easier or more confusing, But when we talk about the voltage of something, we do measure voltage in volts, which means the symbol in the equations and the symbol for the units are the same. And so maybe that makes it simpler, and maybe that makes it more complicated. But you need to know that the unit for voltage is volts. To summarize the three main things that I talked about so far, voltage is abbreviated with the letter V, current is abbreviated with the letter I, and resistance is abbreviated with the letter R. Voltage is measured in volts, which is abbreviated with the letter V. Current is measured in amps, which is abbreviated with the letter A. And resistance is measured in ohms, which is abbreviated with the Greek letter omega. There is an important relationship among these three variables, which is called Ohm's law. So the same ohm as the unit for ohms of resistance. Ohm's law. And Ohm's law says that voltage is equal to current times resistance. And this simple equation, which relates these three variables, is actually going to be one of the more powerful tools that we have to analyze circuits and make measurements of things and understand the relationships between different quantities in a circuit. Let's suppose now that I have a simple circuit, and this is the first time that I'm going to draw a circuit using only circuit symbols. And so this simple circuit is going to contain a battery, and that's what I've drawn on the bottom. The battery has a positive terminal, which is represented by a longer line, and a negative terminal represented by a shorter line that's separated between some distance. And maybe that makes sense because I described a battery as being a thing that separates positive and negative charge. That battery is connected by conducting wires to a resistor, which has some resistance with a value R. And when I connect these things, there's a current that flows out of the positive terminal of the battery in this fashion. And that battery has a voltage that is V volts. So there's a voltage, a current, and a resistance here. So we're saying the battery and the wires don't have any resistance. The only resistance here is of the resistor. Let's say I wanted to make a graph of voltage as a function of current. And so maybe my battery has a knob on it, and I can turn the knob, and as I turn the knob, I'm varying the battery's voltage, and therefore, if I'm providing a larger or smaller EMF, then the current also changes. What Ohm's law really tells us when we write V equals IR is that if, as I'm varying that voltage, and therefore the current, I get a constant slope here on this graph. That constant slope represents the constant resistance provided by that resistor. If I were to write Ohm's law like this, V equals R times I, we could pretty quickly look at that and say that looks like Y equals M times X, or the equation of a line. So I'm plotting on the y-axis, I'm plotting the voltage. On the x-axis, I'm plotting the current. And the slope of that line should be the resistance of the material. And so long as that material's resistance doesn't change, then it's constant, and the slope of my graph should be constant. And we're going to call materials that, when I plot the voltage as a function of current, and we get this constant value of R, a constant resistance, we're going to call those kinds of materials ohmic. O-H-M-I-C. And then there are materials that, as I vary the voltage and the current, the resistance isn't constant. The resistance might do something like this, where the resistance is not constant as the voltage and the current are varied. And maybe it does something else. Maybe it looks like this. And materials that don't provide a constant value of resistance as the voltage and current are varied, those materials are called non-ohmic. So ohmic and non-ohmic. So it's not so much V equals I times R, and as one thing goes up, the other thing goes down. Really what V equals I times R is telling us is that for materials that are ohmic, for materials that follow Ohm's law, V equals I times R, or a graph of V versus I produces a constant slope which has a value of R. And what we're going to find is that most of the objects we'll study are ohmic, or we'll treat them as ohmic, or at least for a certain range of voltages and currents they are ohmic. If we go outside of that, then maybe they're not ohmic, but at least for a certain range where we're going to study them, maybe they're ohmic, and we can use Ohm's law to understand those circuits. The last thing that I'd like to talk about is power. If I look at the little blue circuit that I've drawn, and I think back to the escalator example that I talked about, the battery provides an increase in potential energy, electric potential energy. As the charges move across the batteries, it increases that the energy of those charges, but then the resistor must then be doing the opposite, right? As the charges move across the resistor, there must be a decrease in the potential energy across that resistor, which is why the battery needs to be there in the first place. And we're going to think of these increases and decreases in potential, or increases and decreases in voltage. We're going to call those things voltage drops or rises. So as the charges move across the battery, there is a rise in the voltage. There's an increase, which is why I gave the analogy of the escalator. As the charge moves across the resistor, there's a voltage drop. And over time, you must imagine that if the charges keep rising and dropping as they go across the battery and the resistor, eventually the battery is going to run out of energy. And so where did all of that energy go? And this is where power comes in. As charge moves across an element where there's a voltage drop, and so the wires connecting the battery and the resistor in my circuit have no resistance, and therefore we say that there's no voltage drop, but across a resistor, or maybe more importantly, a light bulb, across a light bulb which acts pretty much like a resistor in a circuit, across that light bulb there is a voltage drop. And as the charges go through that voltage drop, there is power that is dissipated by the light bulb. And you can feel that if you put your hand near a light bulb, especially one that's an old incandescent light bulb. There's a lot of heat coming off of that light bulb. The power being dissipated by that light bulb is equal to the current moving through the light bulb times the voltage drop across that light bulb. And so P equals I times V. A couple things here. First, I is measured in amps and V is measured in volts, but the units of power, instead of amps times volts, is W. And W stands for watts. So the unit of power is watts, which makes sense because we often choose light bulbs based on their wattage, for example. Also, if I know that voltage is equal to current times resistance by Ohm's law, then I can make substitutions into this equation for power by replacing the current or the voltage with its equivalent using Ohm's law. So Ohm's law and our power equation will come back time and time again as we analyze circuits and try to study what's happening.